Hello all and welcome to Physics with Pranav. If you're new to my channel, I'm Pranav and I used to be a CAIE Science and Math student, a tutor for GCSE and A-level students, and an IGCSE World Topper in Science from back in 2013. This video is a part of a series for the CAIE IGCSE curriculum, where for each chapter, I explore key concepts tested, which is backed by data from recent past papers. I dive deeper into these concepts so you have a solid foundation around them, and then I show you how you can apply these concepts in solving past paper questions, which is what we'll be doing in this video. In particular, this video will look at questions from paper 4, which is the theory paper, and chapter 4, turning effects of forces of the CAIE curriculum. If you're a GCSE student but are not studying the CAIE curriculum, don't worry because the concepts that are tested read across to Edexcel, AQA, and OCR. The methodology used to approach the questions will also serve you well, irrespective of the curriculum you're studying in. So you'll be still gaining a lot of value by watching these videos. This video on chapter 4 is one of 3 videos I have made for this chapter. If you want to check out the other 2 videos where I explore key concepts tested and show how they apply to paper 2, the multiple choice paper, please check out the links in my description below. So that said, let's now dive into looking at paper 4 questions for chapter 4 of the CAIE curriculum, which is the turning effects of forces. So we're starting off with October, November 2023. We're looking at paper 4.1. So if I go down to try and find the question on moments. So there's our first question. A radio transmitter is a very tall, thin cylinder. It is prevented from falling over by wires which have one end fixed to the transmitter and the other end fixed in the ground. The ends of the wires and the ground are a long distance from the transmitter. So figure 4.1 shows the transmitter and 2 of the wires. So that's the transmitter. You got a couple of these wires. That's the base. That's the ground. The center of gravity G is shown on figure 4.1. So G is that point there. State what is meant by the center of gravity, right? So center of gravity, we didn't really look at it in the key concepts tested, but I did mention that I will be looking at questions where it has shown up and where you are expected to explain it. So in this case, when they ask what is meant by center of gravity, it is the point on the object where the force of gravity appears to act or where its weight appears to originate from, right? So if you have this transmitter here, although yes, the mass of the transmitter is probably evenly distributed across its entire volume, it appears that the weight of the transmitter acts from this point G. So that is what the center of gravity is. So second question asks, explain why the radio transmitter without the wires is a very unstable structure. So the thing that you need to know about the center of gravity is that generally, when the center of gravity is low in an object, then it is a more stable object. It's an object that is not likely to topple. Equally, if an object has a wider base and a narrower top, then it has a more stable structure, right? If it's going to have, say, for example, you had a nail, a nail that you would use in woodworking. So say you had a nail. Now, if you place the nail with a sharp edge pointing downwards and you have the top of the nail, which has a larger surface area upwards, you'll find that if you let go of the nail, it will always fall because it's an unstable structure. It is top heavy, which means it's got a larger head and it's got a very small nail end. Whereas if you place the nail the other way around, where it was resting on its head, and you had the sharp edge pointing upwards, then you've got a scenario where it's a stable structure, right? Even if you leave the nail, it's not going to topple over to either side. And the reason for that is because the base is now wider. The base is now the head essentially, and it's wider, whereas the top is thinner. So more stable the structure, it will have a broader base, a narrower top, and its center of gravity will be closer to the base. If it's less stable, it will have a high center of gravity, it'll have a very narrow base, or it'll have a very wide top. So in the case of this transmitter, you could see that although the top and the bottom are the same, essentially the same diameter, because it's a constant diameter pole, the center of gravity is really high. If the center of gravity was a lot lower and the base was wider than the top, then you would have had a scenario where it would be a stable structure. But that is not the case. The base is as narrow as the top and the center of gravity is high. So this particular object is not going to be stable, which is why you've got these different, essentially these different wires trying to hold it in place. So that's what I've written here. The radio transmitter pole has a high center of gravity with a narrow base. Such a structure is inherently unstable and requires additional support. So wire W is under tension and it exerts a force T on the transmitter. So, well, essentially that's wire W, and it exerts a force of tension. On figure 4.1, mark an arrow to show the force T exerted by wire W on the transmitter. So if I look here, essentially the tension is going to try and pull the object down, but it's not going to try and pull the object down in the sense that it's going to try and knock it over, but essentially it's directed towards the ground so that the object is tethered. So that's the keyword there. So it has to, so I've drawn it here. I've got like an arrowhead pointing down and I've labeled that T. Okay. So the force T produces a moment on the transmitter about its base. Describe how the moment produced by T is calculated and indicate on figure 4.1 what is meant by any other terms in the description. So the moment of T, i.e. the turning effect that T causes on the transmitter, is going to be equal to the force of T, which is essentially T, which is the tension, multiplied by the perpendicular distance that the force acts from the pivot point. And in this case, the pivot point would be G. G is going to be the pivot because that's where the center of gravity of the transmitter is. So moment of T is equal to perpendicular component of T multiplied by distance from center of gravity. That's just a different way of saying T multiplied by the perpendicular distance from the center of gravity. But you can also say it's a perpendicular component of T into distance from center of gravity. And you'll see the reason why I have laid it out this way. So if I go back up there, we also need to mark where this force acts that causes the moment. So the distance from the center of gravity where the tension acts is that distance there, right? But the tension acts not in a 90-degree angle to the G. So if that's G, and we just looked at how the tension is currently acting, it's acting down wire W, and that angle, as you can perceive, is going to be greater than the perpendicular angle. So we would be interested in the perpendicular distance of the force T from the center of mass. And that essentially is what I've done. I've taken, it goes all the way to the distance that the wire is from the center of gravity, and I've dropped a perpendicular there. And it's that component of T which is going to be the one that you will use when you try to calculate the moment of T. Because although there is the force T, it's not, the force T doesn't act perpendicular to the moment. So that's a key point that I want you to take away. And I've said the perpendicular component of T is T cos A. So I've said here that the angle between the tension and this perpendicular component is the angle from the perpendicular, which I've called A. And based off trigonometry, if I knew T and I knew A, and I wanted to calculate this dark black line here, that would be T multiplied by the cosine of A, because essentially that's the angle, that's the side that's adjacent to it. We've got a right angle triangle here. That's the hypotenuse. So we know the hypotenuse, we know the adjacent side, and we know we don't know the adjacent side, but we know the angle. If we use SOHCAHTOA, CA is essentially cosine is equal to adjacent by hypotenuse. So we know the hypotenuse and we know the angle, so we can calculate its cosine. And if we rearrange for the adjacent, we'd be able to get the perpendicular component of T, which would then be T cos A. Okay, so the last question is around the use of radio waves, which is not a chapter we've done yet, but there will be a video coming out for it soon. Okay, so I think that's all the questions in this paper. So let's move on to the next paper. So the next paper we're going to look at is October-November 2022, variant 4.1. So in this paper, so this is the question that is going to involve moments. It's also going to involve some concepts around force. So rock climber of total mass 62 kilograms holds herself in horizontal equilibrium against a vertical cliff. So that's the rock climber, that's the cliff, that's the horizontal equilibrium. She pulls on a rope that is fixed at the top of the cliff and presses her feet against the cliff. So she is pressing her feet against the cliff. The rope is tethered somewhere at the top. Figure 3.1 shows a position. There's also a clue here where they've said she's got a center of mass at a certain point there, which is 0.9 meters from the cliff face. So that is where her weight will act. We know that she weighs 62 kilograms, so we should be able to calculate her weight, and we should be able to calculate the moment of her weight. That's the information we have so far. We've got a rope, and we know that the rope is being pulled at 60 degrees to the horizontal, and it's being pulled 1.2 meters away from the cliff face. So the first question is to calculate the total weight of the climber. So this is a concept that we looked at in the chapter on forces in motion, where weight is essentially a force. Forces are mass times acceleration. In the case of weight, it'll be the mass times the gravitational acceleration. Usually in your papers, they will tell you what to take as the gravitational acceleration. So if it's pre-2023, it will be 10 meters per second squared. If it's going to be after that, it's going to be 9.8. So in this case, because it's from 2022, it's 10 Newton. It's 10 meters per second squared. So the weight is mass multiplied by gravitational acceleration, which is 62 kilograms multiplied by 10, and that gives us 620 newtons. So that's a weight. State the two conditions needed for equilibrium. So first is that the net force is zero. We've seen a lot of examples in paper 2 where we have a number of different forces acting. If the forces cancel each other out, then there's a net force of zero, which means the object is in equilibrium. It's not going to move up and down, left and right, or top and bottom. We usually don't consider the third dimension when solving these papers, but again, an object can not be in equilibrium if it does move, top to bottom as well. The other condition, obviously, is that the object cannot rotate, so there should be no anti-clockwise moment or clockwise moment, or rather, there can be anti-clockwise and clockwise moments, just like there can be different forces acting on an object, but they have to balance each other out. So, i.e., clockwise moment has to be equal to the anti-clockwise moment. So, climber center of mass is 0.9 meters from the cliff. Yeah, we can see that from the diagram there. Calculate the moment about her feet due to her weight. Moment about her feet essentially means that her feet is the pivot, or the cliff face is the pivot. So we have to take the perpendicular distances from the pivot point when we want to calculate the moment of a particular force. So we know here that her weight is the force that's acting here. It has a value of 620 newtons, which we calculated in part A. It's acting 0.9 meters away from the cliff face or her feet. So she has a total moment due to her weight of 558 Newton meters. Part 2 says the line of the rope meets the horizontal line through her center of mass at a distance of 1.2 meters from the cliff, as shown in figure 3.1. The rope is at an angle of 60 degrees to the horizontal. Determine the tension in the rope. So the tension in the rope acts along the direction of the rope, right? So that's going to be at this angle. And we have always said that when we do moments, the key thing is that we are calculating the force aspect or component that is perpendicular. Or in other words, we want to calculate the perpendicular distance, right, from the pivot. So in this case, the perpendicular distance is 1.2 meters, right? And we know that the rope is acting, the tension, which is the force due to the rope, is acting at 60 degrees to the horizontal. Now, we also know that the climber is in horizontal equilibrium, which is equilibrium with the wall, or the cliff face, sorry. Which means that her total clockwise moment, which is caused because of her weight, which we've calculated in C part 1, which is 558 Newton meters, has to be equal to the total anti-clockwise moment, which is going to be equal to essentially the moment caused by the tension in the rope. But the important thing to understand is the clockwise moment is already, or the force that is acting to generate the clockwise moment is already acting perpendicular to the pivot, whereas the tension in the rope is not. So firstly, we need to calculate the perpendicular component of the tension to the pivot, and that value multiplied by this distance of 1.2 meters has to be equal to the clockwise moment, which is 0.9 multiplied by 62 times 10, which we calculated here to be 558 Newton meters. So we said as a climber is in equilibrium, the anti-clockwise moment has to be equal to the clockwise moment. The anti-clockwise moment is going to be the perpendicular component of the tension multiplied by the distance it acts from, which is 1.2, and that equals to the value we calculated in C part 1. So I've said that the perpendicular component, or I've called it Ty in this case because it acts in the vertical direction, and the y-axis is the vertical axis, is T cos 30. So what do I mean there? So I've just used a little bit of trig to be able to go from T, which is the tension, whose value we're trying to calculate, to try and find the perpendicular component, because we have an equation which links the total clockwise moment, i.e. due to the weight, to the total anti-clockwise moment, i.e. due to the tension. And in order to be able to use that equation, we need to get this perpendicular component. So we need to go from t to the perpendicular component, right? So t is the hypotenuse, and then this perpendicular component is adjacent to the 30-degree angle. And the way I got this 30-degree angle is we've said that the rope is 60 degrees to the horizontal. Then obviously the perpendicular here, which is the vertical, will be 90 degrees from the horizontal. So if the rope is already 60 degrees from the horizontal, then the remaining angle is 30 degrees. So that's how we got this angle here. And then if we looked at SOHCAHTOA, we have to look at the ratio that combines adjacent and hypotenuse, which is the cosine ratio. So if we say cosine of 30 degrees is going to be equal to ty, which is the perpendicular component of t, divided by the t itself, which is the hypotenuse. If we rearrange for that, we get that ty is equal to t cosine 30. And we know that t cosine 30 is what we need to multiply by the distance, which is 1.2, and that equals 558. So if you now rearrange the equation for t, you'll be able to calculate the value of cosine 30 by punching it into your calculator. Just make sure that your calculator is set to degrees and not radians, because we're working with degrees here. So that should give you a value of t of 536.95 newtons, or 537 newtons. So that's the last question in this paper on moments. Let me go to the next paper. So this paper is May, June 2021, variant 4.2. So if you try find the question on moments. So question 2 says define the moment of a force. For these questions, these 1-mark definition questions, the easiest thing to do is just state the formula. So the moment is the force multiplied by the perpendicular distance the force acts from the pivot, or I've just said perpendicular distance of force from pivot. The other thing you could also say is it's the perpendicular component of the force to the pivot multiplied by the distance from the pivot. So either or is an acceptable definition. So the next question goes, figure 2.1 shows an object of negligible weight. The object is in equilibrium, so that's the object, this L-shaped, or rather, transformed L-shaped object. Now the object is free to rotate around its pivot P, which we can see here. Calculate the value of force F. So let's try and quickly understand the system. So we've got a force here, which is due to the weight of this mass of 50 kilograms. The mass is obviously going to act downwards towards the earth, but because it's connected to this pulley system, it's going to pull on this object towards the right. This force, which is balancing it, because we know that the object is in equilibrium, is acting downwards, and we know that, although you might be slightly confused going, wait, so this force is acting downwards, this force is acting to the right, how am I going to go about that? And, if I look at this particular weight itself, it's acting downwards. What's going on here? Yes, the weight is acting downwards, but remember we're interested in the perpendicular distance from the pivot. So if you looked at the direction the weight was acting, the direction the pivot's in, that's going to be parallel to the pivot. But if you look at the way the pulley system is aligned, the pulley system is sort of pulling this way, and that is essentially, if I drew a straight line, if I just extended that dotted line and then went all the way here and went that angle there is 90 degrees. So this 20 centimeter is the perpendicular distance from which the moment due to this weight of 50 kilograms, or rather mass of 50 kilograms, acts, right? And that has to be equal to the moment that is caused by force F, which is acting 12 centimeters away. Obviously, be careful to always use SI units. So that's 20 centimeters, this is 12 centimeters, so that will be 0.2 meters. So centimeters to meters, you've got to divide by 100. 12 centimeters will be 0.12 meters. So then we can say that the total clockwise moment, which is caused because of this weight, because the weight is pulling the object towards the right, and that's going to make the object rotate like that, versus force is pulling it downwards, which is making it go in an anti-clockwise way. So total clockwise moment equals total anti-clockwise moment. The total clockwise moment will be the mass multiplied by the gravitational acceleration to give the weight or the force, and that multiplied by the perpendicular distance, which is 0.2, as we've said in SI units. So that's a value of 100 Newton meters. That has to equal this force here multiplied by its perpendicular distance, which is 12 centimeters or 0.12 meters, which is what I've done here. And if I equated those two together and rearranged to make F the subject of the formula, I get a value of 833.33 newtons, or a value of essentially 833 newtons. That's the value of force F. So if I look at question C, so describe an experiment involving vertical forces to show that there is no net moment on an object in equilibrium. You may draw a diagram in the space provided. So to be able to design an experiment where you want to show that there is no net moment, I think the key thing is, you're going to need an object with a pivot, that's balanced on a pivot, so you can move around freely on either side. You're going to need essentially things that are going to make it move on either side. So you're going to need forces that are going to cause a clockwise and an anti-clockwise moment. And then essentially, the object is in equilibrium when it's balanced, like, when there's no movement in any side, when there's no turning effects in any side. Yeah. And then essentially at that particular point, if you calculated the moments of the two forces that are acting on the object in different, which is making it turn in different directions, that has to be equal. So that's what we've done here. So we've got essentially a bar with a pivot. So set up an object with a pivot, in this case, this bar. Suspend weights of different sizes. So we've got W1, W2, W1 being smaller than W2 at different distances from the pivot, which we call D1, D2. Distance of object 1, let's say, is D1, distance of object 2 is D2. And then we have to adjust their distances from the pivot, D1 and D2, till the bar is motionless. So we have to change these distances. And then at one point, it's like, maybe you've got a seesaw with two people sat at different distances from it, and then it balances out. And then at that point, if you calculate the moments of the two weights at the distance when bar is in balance, so if we tend to do that, we would get W1, D1 would be the value of this moment, and that moment's value is going to be W2, D2. And then at this particular point where the bar is balanced, W1, D1 has to be equal to W2, D2, i.e. the product of this force and this distance has to be equal to the product of that force and that distance, which is where we know that there is no net moment and the object is in equilibrium. Sorry as well, the editing software that I've used has cut out these lines and has changed the formatting that I have, so please bear with that, but it's an issue that I will rectify. So if I move on to the next paper, which is May, June 2020, variant 4.3. So if I go down to try find the question on moments, okay, we've got a question here. It's a center of mass question. So in a double-decker bus, there are two passenger compartments, one above the other. It's very common in Britain to have double-decker buses. So it shows double-decker bus on a tilted platform. That's the top compartment, the bottom compartment. You've got a platform and it's at an angle. The platform is used to test the stability of the bus. The angle the bus makes with the horizontal is gradually increased until the bus begins to topple to the left. Explain why the bus begins to topple is the question. So in a bus like this, the center of mass is usually, it's not quite near the base, but it's not at the top either or the center, so it's somewhere around there. So an object will stay stable as long as if you drew so let's say there's a center of mass there and you drew a line, right? As long as the line passes through the base of the object, that object will be stable. But as you keep tipping the object more and more, the object's base starts going that way, center of mass is still there. And then the line for the center of mass will eventually fall outside the base. And when it falls outside the base, the object will topple. As we increase this angle, we are achieving exactly that. So we have the center of mass, we keep increasing this angle. As you keep increasing the angle, the object's base keeps moving further and further effectively towards the right. The center of mass still stays the same. And then if you drew a line from the center of mass downwards, its center of mass now lies outside the base. And because of that, the object is no longer stable. So that is why when you increase the angle there, you will also decrease the stability of the bus. Apologies for that. Part B says there are 30 passengers in the upper compartment of the bus and 2 passengers in the bottom compartment of the bus. State how this affects the stability of the bus and the reason for this. So what happens is when you put more passengers at the top, less passengers at the bottom, you will tend to move the center of mass up because now the object is top heavy. Yeah, so you tend to move the center of mass up. Now, for the rules for stability are fairly straightforward. You need to have an object that has a low center of mass and has a broader base than its top. So the base is wider than the top, and the center of mass is quite low. You will have an object that is stable. So in this case, we're not changing the base or the top. In fact, this object will have the same size of its base as it does at the top, which already makes it less stable than an object that has a broader base than its top. But the other thing as well is now we have filled out the top compartment, meaning that essentially it's going to be very top heavy. So the center of mass shifts up as well. So what we've essentially done is, because we moved the center of mass up, the bus is now more likely to topple easily. So you can achieve toppling with a lower angle here than you would if there were, say, more passengers at the bottom, which would essentially have the effect of moving the center of mass downwards than it is. So that would be more stable. So by increasing the number of passengers in the upper compartment, the bus becomes top heavy, shifting the center of mass higher. This lowers the stability, as now it's easier for the center of mass to fall outside the base with a smaller angle. So that is essentially what that is. And this, to be honest, is one of the few questions I've seen on center of mass. There's a couple more sections to this question, but again, these sections are dealing with some kinematics and forces. Essentially, the key thing to keep in mind is that for paper 4, you'll find like usually a mix of concepts being tested in every question. So obviously we are focusing on questions pertaining to chapter 4, but as you prepare for your exams, you would have to be looking out for questions from any related topic. So just something to be wary of. So last paper we'll be looking at today, excuse me, is October-November 2020, and we will be looking at paper 4.2. Okay, so that's our question there. So define the moment of a force about a point. So here I've defined it out as a sentence. I've just done this because in summer 2021 question paper 4.2, I ended up just writing the formula out, which is perfectly fine. But for those of you who feel more comfortable writing it out as a sentence, you can do that as well. So here I've just said the moment of a force is a product of the magnitude of the force and the perpendicular distance that it acts from the pivot. So that is essentially what the formula is. So part B, figure 2.1 shows a uniform rod of wood suspended from a pivot. Okay, so that's our system there. It's very important to locate the pivot, so that is not the pivot. The pivot is right there at the top. You always have to remember that any time the pivot is not at the center and is acting at one of the edges, you have to take into consideration the effects of the center of mass of the object. So in this case, you've got center of mass marked out. They've also shown you clearly that there is the weight of the object that is acting downwards. And the center of mass is 0.25 meters from the pivot. And there's a force F that acts 0.75 meters from the pivot, and it acts horizontally. Okay, the rod is held stationary by a horizontal force acting as shown. The mass of the rod is 0.08 kilograms. Okay, so this force W is trying to pull the rod downwards. It's trying to induce a clockwise moment, and this force F is trying to stop that clockwise moment, and it is trying to do that with an equal and opposite anti-clockwise moment, which is what I'm guessing would be expected to calculate. So the first thing is they want you to calculate the weight of the rod. This is from chapter 3, forces in motion. So we know that weight is a force, which is the mass multiplied by the gravitational acceleration. Because this is a pre-2023 paper, the gravitational acceleration will be 10. So the mass is 0.08 multiplied by 10 gives you 0.8 newtons. That's that weight. The moment of W about the pivot. So essentially here, W in itself is not acting perpendicular to the pivot, right? Because if you took the pivot, it's only a force that would act like that. That would be perpendicular. So if W acted like this, it would be perpendicular, but it's clearly not acting that way, which means you need and there's no way for you to be able to easily calculate the component of W that acts perpendicular. So the easier thing to do is to use the perpendicular distance that W acts from the pivot. And essentially, you could see that if W were to act in the perpendicular direction, then you would have a longer distance, yeah, because the length of the rod from the pivot to W is longer than 0.25 meters. So the fact that it's not acting that way essentially is the equivalent of a perpendicular force to the pivot that is acting at a shorter distance from it, which is 0.25 meters. But anyway, for the purpose of this question, we know the weight and we know the perpendicular distance from the pivot, so we need to know either one of the two, and we are given one of them. So that's going to be 0.8 multiplied by 0.25, which gives me a value of 0.2 Newton meters. So that is the moment. They want to know the moment of F about the pivot. So they want to know the moment of F. We know that the rod is held stationary, which means it's in equilibrium. It's not swinging in any way. So the moment around F has to be equal to the moment because of W. So that would also be 0.2 Newton meters. Finally, they want you to calculate the force F. So to calculate the force F, again, you need to know the force multiplied by the perpendicular distance, or you need to have the perpendicular component of the force multiplied by the distance, either or, really. So in the case of F, again, if F were to act perpendicular to the pivot, it would have to act in that direction. So it would have to be pointing upwards like that, essentially pointing towards the term that goes rod of wood. It needs to go there, but instead it's a flat horizontal force, so it's clearly not perpendicular. But then this distance that's given here, that distance makes a nice 90-degree angle between the pivot and the force. So if you think about it, it's literally a right angle triangle. If I moved this 0.75 to here and drop it there, then it nicely connects with force F, which is perpendicular to that. So that is the perpendicular distance. So they've given you the perpendicular distance again. It's always a good check to do that. Essentially, if I want to know if I'm not thinking that the force is perpendicular and they've given me a distance and I want to see if I can use that distance, the best thing to do is to, from the pivot, draw the distance the way it is, in this case 0.25 meters, and then draw the direction of the force, in this case W, and if it forms a right angle triangle, then you're fine. And in the same scenario here, although F is clearly not perpendicular to the pivot, if I were to join it with the distance given, which is 0.75, it's not giving you the distance of the rod or distance along the rod at which F acts, but rather the distance down like this. And then if I drew the direction of F, and if it forms a nice right angle triangle, then essentially what I've got is the right distance. I would be able to calculate the moment. So moment of F is equal to F multiplied with the perpendicular distance from the pivot. We calculated what the moment should be based on the equilibrium concept. So we know it's 0.2 Newton meters, and then if we rearrange, and we know the distance as well, the perpendicular distance. So if we rearrange the formula to make F the subject, we get a value of 0.267 newtons, or roughly 0.27 newtons. The last question asks, the angle between the rod and the vertical is increased. State whether the force F needed to hold the rod stationary must be increased, decreased, or stay the same, right? So explain your answer. So essentially, this angle is increased, yeah? So what that essentially means is if I'm trying to keep the perpendicular there, if I move this down, if I move this downwards like that, that way I would tend to increase the angle because now the rod is pointing somewhere there. So this angle automatically increases, right? If the rod is pointing somewhere there, then the distance from the pivot to the force will also tend to increase because now it's 0.75. If I made this angle smaller, so if I lifted it up like that and made this angle smaller because now the rod is pointing like this, then that distance shortens as well. But if I want to increase this, then I need to move the rod down, and that increases the distance from the pivot. So when the angle is increased, the distance between F and the pivot increases, or the perpendicular distance rather, to be more accurate. So if F was the same, the rod will not be in equilibrium as its moment will now have increased, because if I use the same value of F, it's acting now at a greater distance, which means, the mass of the rod or its weight will always stay the same, right? Unless you do something to the rod like chop it in half. So if I kept F the same, the rod's then going to start moving in an anti-clockwise direction. So I would have to now adjust F so that it is still keeping it stationary. So F needs to be decreased to maintain the same moment when the distance increases. So you need to decrease F. That is the key concept there. So that's the last of the paper 4s we'll be looking at for this chapter. I hope you found this video useful, and if you did, I would appreciate it if you can like, share, and subscribe. And obviously let your friends who may benefit from it know as well. Thank you very much, and I will join you in the next video. Bye-bye.